How are you, everybody who is watching this video? I would like to take this opportunity to welcome. We have a local students, and also for you who is not a part of this class, you're only welcome to learn the beauty of electronics engineering. My name is Olenjolai, and I'm very happy to have you today. I have some local students who are doing undergraduate studies in one of the institutions in Tanzania. So we have been learning about how we can solve a real-life problem. And actually, the problems that we are solving or we have decided to solve step by step is actually about how we can boost the signal which is attenuating when we transmit the audio signal for the long distance. So when we have just done I'll follow some principles of design, then we reach the point of the design. So that's why that I would like to welcome you into workshop 5. We'll be focusing on designing the linear power supply, where we are going to have a theoretical part, and then we'll go for the simulation, and then we'll go for the power supply. So I believe that you're well prepared, so let's go to the business. So the quick review of the workshop 4. Actually, what we've been doing in previous workshop, we have been opening the detailed block diagrams of linear power supply. So the first block, we say that here we are going to have an element, electrical components that called the step-down transformer. And then the second one, or the second block, here we are going to have a rectifier unit. Okay? Then the next block, we are going to have a filter unit, which we have already discussed about these 3 blocks. Then the next one is about voltage regulator unit. And then the last block is load. So load, it can be a circuit, it can be a system, it can be a subsystem. So when we say load, actually it can consist in any of those parts. So we've discussed about this block, we opened this block, and then I left the homework in this block. So today we are going to focus on voltage regulator unit, and then drawing the overall schematic circuit diagrams of the linear power supply. So before I go, or I move, or I keep on, I think that let us do or review some few concepts. So in case of the rectifier, or what we've been discussing, just to remind you, we chose a step-down transformer of the following specification, where that the root mean square voltage, the input root mean square voltage, it's 220 volt, and also the output will be 12 voltage. In case of the currents, means that we say that we have chosen the step-down transformer that provides 1 ampere. So that's the important parameter. But again, in this block of rectifier unit, we say that we are going to choose the bridge rectifier. So the bridge rectifier actually is the arrangements of the 4 diodes. And then we did not discuss about, because you can build a bridge rectifier by using a bridge rectifier IC, or by using the individual diodes. So the next concept that we have discussed about what, because we say that bridge rectifier actually rectifying the voltage, or we say that this bridge rectifier will receive the maximum voltage of 16, according to that step-down transformer that we have chosen, 9.7 volt. This is the input of the bridge rectifier. Then we say that the maximum voltage, or the out of the bridge rectifier, once we did the computations, is 15.57 volts, something like that, about that. But also, we've been presenting our informations in tables. So we have reduced the table 1, and also we have reduced the table 2, and I left the table 3 to be the assignments for the students, including the physical students and even online students. But again, so we've been discussing about graphs. So we had the graph, we had the figure 1, which actually presenting the input voltage to the step-down transformer and the output voltage. So we had the figure 1, and also we had the figure 2, which actually representing the graphs of the input to the rectifier unit and output to the rectifier unit. So we have discussed a lot of the information and a lot of things, but finally I left the homework. For all students. The first 2 questions, and that homework was actually about the filter unit. The first 2 questions, I asked the students to choose standard capacitor that we have to use. And then the second questions, I told the students to draw the table of result. Table of Then the third question, I told the students to draw the graphs of 40 rectifier unit. So I don't know whether you have done it or you didn't do, but let me hear from you. So before we start today's workshop, this is all about workshop 5. And in workshop 5, we are going to deal workshop 5. So you say that design of what? Design of voltage regulator, voltage regulator unit. Voltage regulator unit. So before we start our today's workshop, let me just appreciate and acknowledge the presence of the local students who have a very good smiling faces today when they come for this class. Good afternoon, class. Good afternoon, class. Are you ready? Yes. Are you ready to write, or you are ready to understand before you write? Okay, give me the feedback about the homework. Did you do the homework? Did you do the homework? Others yes, others say no. So why didn't you do the homework for those who didn't do? The questions were tough? Or you found confusion? Huh? Or you don't like homework? Do you like homework? Eh? Okay. So the class is quiet. Okay, so let us wind up about what we've been discussing yesterday, because we need these information in order to cover these concepts in practical and even in simulation. So the table of resulting, so this is table. I think that the first questions are, means that the first questions we say that choose the standard capacitor or electric capacitor. I told you the standard electric capacitor because you cannot find electric capacitor suitable for what? For filtering. So we said that yesterday, in case that you have to know different values of the standard capacitors, we said that suppose you have the minimum or the electric capacitor which has a capacitance less than the calculated one, and then here we are going to have C2, and here we are going to have C3. So C1 for the capacitor that we computed, what the calculated value? 4,860 microfarad. So, and then so 408,600 microfarad. So the next, the previous capacitor for this one is 4,700 microfarad, and for C3 it is 5,000 microfarad. So I told you that we prefer to choose the capacitor which has capacitance higher than the calculated. Okay? So simply say that the standard capacitor is used to filter the ripples in the C signal. The C signal is capacitor with capacitance of 45,000 microfarad. Okay? Okay, class? Okay? So this is correction. Correction of the homework. I told you that capacitors, resistors, inductors are manufactured based on the standard values. They are not manufactured for any value. And there is a principle used there in order to make sure that the available capacitor fits for any design that you have. So it doesn't mean that because the capacitors or resistors or inductors are built or are made according to the standard value that you cannot, you are limited to use that standard value. No. You might do your designs and your calculations and have the final maybe having the capacitance or resistance or the inductance, which is not lying between the OT, or which is not standard. So the principle, I don't want us to talk a lot. For instance, this capacitor of 500 microfarad will have something we call it tolerance. So because this is the typical value. In engineering, we used to have something we call it minimum value, and also we used to have something we call typical value, and also you have to use something we call the maximum value. So for instance, this capacitor has 5,000 microfarad. But this is the typical value. So it means that the way it has been manufactured, there is a tolerance, because we say that in engineering, any physical quantity without unacceptable errors is meaningless. You have learned the subjects of errors in dimensions and error, right? That subject is very important in engineering. Because for instance, if I do that, I say, I measure the capacitance of the capacitor. Then I say that what I found after measuring by this capacitance meter is 5,000 microfarad. This is meaningless in the world of engineering. This is meaningless in the world of science. We cannot measure the capacitance of the capacitor and find 5,000 microfarad. It's not possible. We should also include the errors, the tolerable error. So for instance, if I say that I measure the capacitance of the capacitor, then I found that 5,000, let's say, plus or minus 0.2 microfarad. So this is acceptable in science and acceptable in engineering. Okay? So what does it mean? So this means that the capacitance, it means the minimum value of capacitance is 5,000 minus 0.2, then microfarad. So this is the minimum. So it means that this 500.20. So it means that if you're presenting here, it means this is 5,000 minus 0.2. That will be minimum. This is the typical. Microfarad. For the maximum value or tolerable or maximum value of this, of the capacitance of this capacitor, it will be 5,000 plus 0.2 microfarad. So the concept of tolerance is the one that gives us evidence to say that we computed the capacitance of the capacitor and found it is 4,860. When we use the capacitor of 5,000 microfarad, we are still within the range. Because this one has the minimum value and maximum value. And that's what you have to know. Okay, class? Are we together? Are we together? That's the principle we use for the capacitor. That's the principle we use for the resistor. That's the principle we use for the inductor. Okay. So we'll discuss later in other workshops, because just I've tried to touch. When I teach you the concepts of tolerance right now, we'll deviate from the concepts of design. Okay. So then the second question was what? Draw what? The table of result, table of result of 40 filter unit. Table of result of filter unit. Your table, whatever the case, should have 4 columns. So the first column, and here we have the second column, and here we have the third column. So the first column we use called the electrical parameter, which hopefully I know that you have written it. So now what are you going to write? That's another story. But write the electrical parameter, I know that every student wrote it. Then here we are going to have calculated the value. Calculated the values. Then at this point we are going to have what? Simulated the values. Simulated values. Then at this part we are going to have what? Measure the values. Measure the values. So the first one, we say that capacitance. Capacitance of the capacitor. So capacitance, when we calculated, we found 4,860 microfarad. But we say that's not the standard. So theoretically, the capacitor we are going to use, we have been told by the manufacturer it is 5,000 microfarad. Right? in simulations, we don't focus on measurements. I don't think that, because in simulation we have also measuring instruments. But in most cases that we just take a capacitor of the standard value. So we don't have, most of the simulation tools, they don't have capacitance meter. But in case of the measured value, we'll have a capacitor. We'll have a capacitance meter. So now the issue is whether the capacitance meter can measure that capacitance of the capacitor or it can't measure. So filling the next two columns depends to the efficiency or capability of the measuring instrument. But again, we say that we had what? We had the maximum, the input maximum voltage that we fed to the rectifier unit. How much was it? Which is the output of the filter unit. How much? 15.57 volt. So when we do simulations, we'll measure the output voltage after the filter. And then so when we do the, just we build this power supply, we'll measure also practically. And then we say that we have output maximum voltage. So we say that, theoretically we say that the filter will just draw some AC components which do not contribute anything to the maximum point or to the maximum voltage, because those AC components are the ones that you used to see. Because remember that when we do the ripple, then here it's a maximum. Okay? Yeah? Yeah? So this here is a maximum. So these other points are not required. So there's no any change, theoretically, there's no any change of the maximum voltage. So when we do simulations, we also observe. Are we together? So these are the important parameters. These are the important parameters. So table, always we label table where? At the top, eh? Do you remember? Table 3. The table, the what? How do you call it? Eh? Table of what? Table of results. So 40? Filter unit. Ask your neighbor, are you a filter or are you a rectifier? Ask your neighbor, are you a filter or a rectifier? What did he or she say? Rectifier or 4 diodes? Okay, so before I talk about what is happening for the AC and DC, let me go straight forward to the question 4, to the question 3. Then I'll talk something there. Draw what? Draw the graph of what? Of rectifier unit. I heard that somebody has a question, so don't think that I didn't hear. So for the nature of this graph, okay, think that because we are drawing together, Ask it. Ask it loudly so other students can hear your questions and possibly can give you the response. What? Mm.
So the question is that voltage is the one which will enter to the filter unit and will be the unit at the filter unit. And we have said that voltage will remain the same if the input is down. Absolutely understood.
I will explain later. Very soon. I told you to put the computers away. Okay. So those are the graph. So Mikidadi, how do you draw the graph within your computer? But the challenge, I know. Writing is fine, but drawing is another story. You draw. Can I see? So you are drawing now. That is good. Okay. So, okay. This is filter. Sorry. So Abdullah corrected me that I just made a mistake, not rectify. This is filter. But others, they are still copying. And when they copy, they assume that I will revise it later and they understand it. Okay, so stop writing. So we fed this pulsating signal into the filter unit. I say stop drawing, stop doing with anything that you are doing. Stop. Yes, stop writing, stop drawing. Listen. So this is what we have got from the rectifier unit. Right? Right? And then once we fed this pulsating signal into the rectifier unit, then we have the output which is unregulated DC voltage. And the nature, you might find that, okay, it is kind of DC, but still changing. Because unregulated, it means that the value of the voltage is still varying. Don't worry about the magnitude, whether it is 15.57 or volt or whatever, but the nature of the signal, because most electronics and telecommunications components or devices or system needs the constant or needs the regulated power. In case there is a alternations of the power, then you find that most of the components might be malfunctioning. So that's why that the output of the filter is still not convenient to feed directly to the load. Are we together, class? Are we together? We are trying to tell you that what is going on within the particular unit. And it's better for you to go and verify. Struggle your level best to make sure that you verify what we are telling you or what we are trying to convince you to accept. So another concept, so these are the kinds of the graphs that you might find them, you might see them. If, for example, that you do good setting, you might see them practically. So another piece of the information, so another question, so another concept, or another question, how do we connect? How do we connect? Because when we answer that question, because I know some students are asking themselves questions, how comes that the AC component has been removed? The input voltage is 15.57 volt, and the output voltage is still 15.57 volt. How comes? That's the questions that might kick in or might kick in the serious student, in the mind of the serious student. So this is the point. So we can have also question 4. How do we connect the, not how do we connect. How does the electrolytic capacitor filter the pulsating signal? Why should we ask ourselves these questions? Very important. Because we said pulsating signal, class A pulsating signal. Again. Eh? Examine your neighbor if he or she is pronouncing. Say pulsating signal. Again. Ruben, yourself. Eh? Say pulsating yourself because you are not saying. Eh? Again. What is pulsating signal? Class, say pulsating signal. Again. Loudly. Precious alone? Precious is not in the class. Come back to the class, Precious. Precious is thinking the tiredness. Like the last Friday's tiredness. Okay, so pulsating signal, simply say that it is the combinations of the DC signal plus AC signal. Okay? Eh? Yes. So when we have the output from the rectifier unity, we have the combinations of DC signal and the AC signal. Then we feed the C signal and the AC signal into the capacitor. So the question is, how does the capacitor draw the AC signal and leave the DC signal? Because from there, you might get the answer, how comes that the input voltage to the filter unit is the same with the output voltage to the filter unit? Okay? 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 So, first of all, we say that the capacitor must be connected in parallel. In parallel to the rectifier unit. We don't connect this capacitor in series, so it should be connected in parallel. Why should it be connected in parallel? In order to establish two roots, so we are going to have a junction. Hey! We are going to have what? Yeah? We are going to have a junction. So when we have, for instance, this is the signal from the bridge, from the rectifier unit. This is the bridge or rectifier unit. So now we have the output. So you are going to establish a junction. One junction will be for the unregulated DC signal, and another junction will be for the AC signal. Are we together? Are we together? Are we together? So that's why we say that the capacitor, first of all, must be connected in parallel. Why should it be connected in parallel? Because this is the network. So if this is the junction A, we are going to have this network and this network. So this network will have unregulated DC signal, I've written here, and then the other network will be for the AC. So remember that at this point, when we talk about the maximum voltage, we are talking about the DC. So we didn't include the AC components when we calculate the maximum voltage. Okay? Okay? So if that's the case, we say that this AC, this is the point where we have to connect the capacitor. So stop writing, look on the blackboard. We are not drawing the schematic circuit diagram yet, but I want to explain you, just to tell you, or to give you some reasons why the capacitor will remove AC components and leave the DC component. So this is the rectifier unit. This is the output of the rectifier unit, which is pulsating signal, and here we have a junction. So in this junction here, we are going to have a capacitor, which is a filter capacitor, right? And then on this side, we are going to have what? DC signal, which is still unregulated. Okay? Okay? So, if that's the case, you say that here we have what? AC signal. So you have AC signal and DC signal. So the question comes in the mind, how comes that, for instance, at this point, we have AC plus DC. So what happened? So that we have DC on these roots, and we have AC on this root. That's a very important question. From there, you'll get the reasons why did you write the input maximum voltage is still this one, or just equal to the input voltage to the filter unit is still what? 15.57, and the output is still 15.57, because this is actually, we are talking about DC. We are no longer talking about AC. Okay? Okay? Okay. So if that's the case, you say that we have to go back to the scientific theory, and especially to the theory of what? To the AC theory. AC theory. So you have to go back to the AC theory in order to get the answer of that question. So in AC theory, we taught you about three electrical components. The first one is resistor. The second one is what? Is capacitor. Stand up. Oh, sorry. Sorry. Stand up. Okay. So the first one, we discussed about the first one is resistor, the second one is capacitor, and the third one is what? Is what? Inductor. Okay? So if you do remember that, we have taught you about the mathematical equations of resistor, capacitor, inductor. And if you do remember that, we taught you also about R, L, S, R, 10. R, L, C, 10. Right? So from there, we have just taught you something, how we can, because the capacitor provides, or the capacitor store charge. But also it provides capacitance to the any signal that's flowing within it. And that capacitance, we call it, or that capacitance, so we call it capacitive reactance. So when the capacitor store charge, but now when you allow electric signal to pass through the capacitor also provide capacitive reactance is it's a resistance in nature. So then we told you that the capacitive reactance of the capacitor is equal to 1/2 pi times frequency of the AC signal times capacitance of the capacitor. Do you remember that formula? Class, stand up. So we have learned this formula in AC theory. Kevin! In AC what? Theory. Capacitive reactance is equal to what class? 1 over 2 pi times what? Times what? Capacitor or capacitance? Capacitance of what? Of mangoes? Capacitance of who? Capacitor. So, in order to know that, and this will give you a reasons why in most cases even coupling, input coupling and output coupling of the capacitor, they don't allow the DC signal to flow back or to flow to the directions where it's not desired. So here's the reason. So for the AC components, which are outputs of the rectifier unity, the frequency is 50 Hz. So if that's the case, it means that the capacitor, this electrolytic capacitor will provide it provides capacitive reactance to the capacitor, because it will be 2 pi times the frequency, which is 50 Hz, times the capacitance, which is 5,000 exponent negative 60 farad. So from here, you can compute the capacitive reactance of that capacitor. Okay? This is for what? For AC signal. For DC signal, the frequency of DC signal is 0 Hz. So if we calculate the capacitive reactance of the DC signal, then we have 1 over 2 times pi times 0 times what? 5,000 exponent negative 60 farad. So for this case, it will be 1 over 0. And for this case, the capacitive reactance of any of electrolytic capacitor against the DC signal is infinity. So if it is infinity, any electrical or electronics components which has infinity resistance, it does not allow electric signal to flow through it. Okay? So whenever you feed AC and DC signal to the capacitor, the AC signal will flow because there is a minimum resistance against it. But the DC signal will never flow because the DC signal will face infinity. Infinity. It's just like if I ask all the students to push this wall until it fall down. Can you? Okay, now push the wall until it fall down. When it fall down, you go back home. It will be the end of the class. So you cannot push the walls to fall down. Why? Because to provide resistance against your push. Are we together? Are we together? So for this case, because here we have AC plus DC signal, at this junction, the AC signal will be flowing towards the capacitor, while the DC signal will face infinity resistance. So it will find only the alternative, or the roots is just the roots towards the regulator unit. So in most cases, AC loves capacitors. Because if you compute it, this resistance is very small. How much did you find? My friend there. What's your name? Pardon? Aaron. Caroline. What did you find? Because I saw that you have took a calculator. Not Winfrida. Winfrida is busy. 0.6 what? Ohms. If you calculate this one, what do you get? 0.6 ohms. 31? I have very interesting students in this class. So this guy has got 0.636. 2 times pi times 50 times 5,000 exponent negative 6. Then reciprocal. 250 pi times 50 times 5,000 split negative 6. Then we find reciprocal. I got 1.57. Huh? Huh? 2 times 5. What did you get? Oh, you are just writing. One over the answer. I got 0.636. So this one is 0.637 ohm. Why it is ohm? We had the Faraday over second. What do you get? Faraday over second, because the center of frequency is per second. Huh? Faraday over second. So simply we have second over Faraday. So here we have second over Faraday. What is Faraday? Or what is capacitance? Quantity of charge over what? Over voltage. So it means that the quantity of charge, which is Coulomb, over voltage. But what is the quantity of charge? You don't bother yourself. You just know resistance, ohm, is over. What is the quantity of charge? In other words, you say this is second, quantity of charge is current times time, which is ampere times second, divided by what? By voltage. So second and second cancel. So you have 41 over ampere over voltage, which is equal to what? Voltage over ampere. So voltage over ampere is equal to what? Yes. That's how. For you, you just write ohm, but if somebody challenge you, show me how the units have been converted to ohm, you say it is ohm. It's always ohm. You want to complicate. Class, is it clear? Yeah? So remember that the maximum DC voltage, which is the output of rectifier unit, is DC. So that's why that the input into the filter still 15.257 volt, and the output still 15.57 volt. So here we have to say that this is against the DC signal, and this one is against the AC signal. So having a resistance of 0.637 is just a very small resistance. Right? Right? Yes, very small resistance, even 1 ohm. That's the principle or the working principle of capacitor against AC and the DC signal. Keep it in your mind and never forget it. Okay, so if that's the case, is there any questions about filter unit? No questions. Thank you. If you have any questions, I know that you might have some other questions, but you may ask them later. So number 4, let us go to the voltage regulator, voltage regulator unit. Voltage, say voltage regulator unit. Say it loudly. Voltage regulator unit. Precious is not writing today. Kevin is wonderful. Huh? Okay. So in voltage regulator unit, we say that the output of, or the output voltage of filter unit is unregulated. So say the output voltage of the filter unit is unregulated. Unregulated. So you say that most electronics devices and equipment. Consume or needs the constant regulated voltage, okay, voltage from the power supply unit. So say most electronics devices and equipments need the constant regulated voltage from the power supply unit. So you say that a voltage regulator is the integrated circuit or IC that consists BJT transistor, bipolar junction transistor, capacitors, and the resistors. So a voltage regulator is an integrated circuit. Say integrated circuit. Say integrated circuit. So it has 3 terminals, but within it consists a number of bipolar junction transistors, a number of resistors, a number of capacitors. For instance, the low power voltage regulator of 1 ampere or 1.5 ampere consists of 15 bipolar junction transistors. How many? 15. Up to this time for you, how many bipolar junctions can you use in the circuit? Even 1 bipolar junction transistor, it's a challenge for you. Is this it? Oh, now you have mastered, so you can build a a cascaded voltage amplifier. So you say in electronics, engineering, we have positive voltage. We have the following types of voltage regulator. So these are only regulating voltage regulator. The first one, congratulations, positive voltage regulator. Positive voltage regulator. Second one, Abdullah. What is going on? Voltage regulator. Not what is going on with your lens. What is going on with your mouse? And the second one, we call it a variable voltage regulator. So I'm trying my level best to give you an overview about voltage regulator because it's very important part of linear power supply. It's very important part of the switched mode power supply. It's very important part of the DC power supply. Positive voltage regulator. Say positive voltage regulator. Positive voltage regulator. Negative voltage regulator. Variable voltage regulator. Again. Shake your neighbor. Again. So say positive voltage regulator, negative voltage regulator, variable voltage regulator until you dream it tonight. So let us start with variable first because okay, say variable voltage regulator, negative voltage regulator, positive voltage regulator. Dennis, your friend is not saying. Abdul. Can I do something for him? Huh? No. Why? He's sick since yesterday. Again, pronounce it. 1, 2, 3, let us go. Haya. Siku utazikumbuka hizi. One day you remember this stuff that I'm teaching you. In manufacturing, we say that, so, we'll be focusing, in this workshop, we'll be focused about positive voltage regulator, negative voltage regulator. I'm not going to touch about variable voltage regulator because we are going to design the fixed voltage linear power supply. We're not designing about variable voltage linear power supply. But the electronics workbench that you used to have in workshop, it's variable. Variable power supply. Right? The difference, this one gives you the positive voltage, this one gives you the negative voltage, and this one gives you either positive, most cases it's positive, but it's varying. From 0 volts, the maximum, most of the power supply provide up to 30 voltage. So this one, it can provide you from 5 volt up to 24 volt. And this one also it can provide from negative 5 volt up to 24 volt, negative 24 volt. And this one can provide 0 volt up to 30 volt. That's the range. So they say that, but this is fixed. Remember, this is fixed. It means you may have voltage regulators of 5 volt, or 6 volt, or 7 volt, or 8 volt, or 9 volt, or 10 volt, or 12 volts, or 15 volt, or 18 volt, or 24 volt. Okay. So if this is the case, now we say that the positive and the negative voltage regulator, I see, when you say integrated circuit, I say, for instance, the positive voltage regulator, it has 15 transistors within it. It's small when you see it, but what is hidden within it is wonderful. And most of those transistors, they work at the switch. And they have a different configuration. I will share with you the data sheets of LOM38XX series. And within that data sheet, it shows the schematic. We call it a functional block diagram of the integrated circuit. Okay? So the positive and negative voltage regulator ICs have 3 terminals. Have 3 terminals. How many terminals? 3 terminals. Ask your neighbor, how many terminals do you have? If a positive volt and negative voltage regulator have 3 terminals, how about you? How many terminals do you have to conduct biological power? So what did your neighbor say? Many. For instance, if you want to eat ugali, how many terminals do you use? Many. Because you have to regulate the food within your hand, isn't it? You are using spoon, Big knife. You're using spoon, eh? Not fingers. Why? Okay. So we say the positive and negative voltage regulator, I see, have 3 terminals. So you say that according okay. So you say that series of voltage regulator. Why do we specify about voltage regulator? Why don't we call it just a regulator? Because in electronics, you can either regulate voltage, or you can either regulate current, or you can either regulate power. Right? So the word voltage regulator is very important. Because when you encounter another types of regulator, you should not limit yourself. We are always regulating voltage. No. In case of power, we are always regulating voltage. But in case of other tasks, we might regulate currents, we may regulate power. Right? And that's why that we have voltage amplifiers, we have current amplifiers, we have power amplifiers. Which one do you know? None of them. So you say that the series of positive voltage regulator is LOM78XX. Did you understand or you didn't understand? You didn't understand, but in Tanzania we used to write. We don't care whether we understand, whether we understand or we don't understand. We used to write everything written on the blackboard. Because in Tanzania, many students have a concept that it's not important for understanding to come now. The understanding might come even later on, when I be reviewing. So say LOM78XX. LOM78XX. Again? LOM78XX. So ask your neighbor, what is your series? This is the series of the positive voltage regulator. Ask your neighbor, what's your series? Not series at the movie. Okay. So what does this mean? So when you say series, means that the compounds, first of all, there's the compounds, there are different compounds which are using this. LOM, listen, hey! It's an M40. You find that it's abbreviations of the manufacturers. No, we call it IC. IC, identity, letters. Because this is what we call the IC number. Okay? Then 78 is a number notated for the positive voltage regulator worldwide. And then X, it depends to the type of the, to the amounts of the regulated voltage that will be provided by a voltage regulator. And this X also depends to the amounts of the voltage which will be provided by that voltage regulator. So stop writing and look on the blackboard. Let me give you examples and explain the meanings of this series. So some examples, you say that in electronics, we have a voltage regulator, positive voltage regulator, which is called LOM7805. You see, remember that the series is LOM78XX. Wait! So X here is 0. The second X is what? A5. The second example, we have also LOM7806. What does it mean? This 05, it means that it provides the positive 5 voltage, which is regulated. What does these two numbers mean? This one will provide the output voltage or output regulated voltage of 60 volt. Okay? But it's fixed. It does not vary. Then the third example, we also LOM 7807. I said stop writing, stop drawing, and stop slumbering. Look on the blackboard. So then we have a fourth example, LOM 7808. Then we also have the fifth example, LOM 7809. So these provide 80 volt, 7 volt, 9 volt. Okay? Then we say number 60, we have LOM 7812. We don't have LOM 7811. So don't cram. That will be adding by one, adding by one, adding by one. Because in Bongo land, we cram. So you just learn these 5 and then you say, so now I understood. I got revelation. So for the voltage regulator, you just say add the one, add the one, add the one, add the one. No. Because we don't have anything, we don't have a voltage regulator which does not have a particular function. All of these standards have been set according to what amounts of the voltage we use in operatings or different electronics devices and the equipments uses for the particular functioning. Because for example, a television receiver, it consumes different voltage in different sections. Even your mobile phones is consume different voltage in different sections. So all of those voltage regulators have been manufactured for the particular purpose. They are not manufactured for just for leisure, or just to tell you that you have a voltage regulator of LOM 7811. Wewe, Mwatatu, and your neighbor. Your neighbor on your left hand side. Then the seventh example, LOM 7815. Give me a pen. And then so from there you listen. Precious, keep yours. Number 8, LOM 7818. When I ask you to be attention and focus and listen, look, these are the information which do not need you to repeat several times. For instance, myself, I learned 9 years ago, and then it's stuck in my mind. It's not the information that you have to go and restart and restart. When you listen careful, you just keep those numbers. They are not tough. So when you think about linear power supply, you have to know what are the available voltage regulators. Okay? Then the last one, that's example 9. The last one, we have LOM 7824. Forget these standards or forget. Don't relate it what the voltage regulator provide with what the step-down transformer provide. We have spoken about the specification of the transformer. We are done with step-down transformer. Now we are talking about voltage. Voltage regulators. Are we together? Are we together? Eh? Yeah. But in our country, this is the mostly found. This one, this one, this one. You may find this, but they are rarely used. Possibly this one. Okay? Okay. So that is LOM 7886. Okay? So right now, because I know that you have a hunger. You are hungry in writing. Especially if you understand. You say, let me write. Okay, right now. Because usually in Tanzania, we don't tell the students write. They just write themselves. Why? They believe in writing rather than in understanding. Then we say that the standard series of negative voltage regulator. Regulators I see is LM79XX. So now it's the time where I want to tell you that stop writing. I didn't say stop writing. I'm about to tell you that stop. But others, they have already finished it to copy. So we mentioned about negative voltage regulator. Ask your neighbor, where do you use them in electronics? Huh? Where do you use them in electronics? If I just remember about the amplifier, the transistor, the amplifier, we always use either positive 12 DC or positive 15 or positive 18 volt DC. Where are we using these negative voltage regulators? Where do you use in electronics? I said, ask your neighbor. I said, ask your neighbor. Ask your neighbor. What did they ask your neighbor? What did they told you to ask your neighbor? Because I asked you to ask your neighbor to give you an idea where do we use negative voltage in what? In electronics. So, but Johanna was concentrating on what? On copying the notes. So I asked him to ask his neighbor. Then he said, ask what? Okay, so examples. Hey, stop writing now. Check your neighbor, take your neighbor's pen. Take your neighbor's pen. And it should be black and yours should be blue. So the examples are just like it this way. So we have LM7905. So this one, when we discuss about the output voltage, let me just add something. Output voltage. So for the output voltage for this case is 5 volt, positive 5 volt. This one positive 60 volt. And this one positive 7 volt. And this one is positive 80 volt. And this one is positive 9 volt. And this one is positive 12 volt. And this one is positive 15 volt. And this one positive 18 volt. And this one is positive 24 volt. So for this case, here we have what? LM79XX. And here we want to discuss about output voltage. So for this case, we have LM79. Check your neighbor if he or she is listening. Check your neighbor. LM70 what? 0 what? 5. So this provide negative 5 volt. The next example, LM79 0 what? 06. Negative what? 60 volt. Then LM79 0 what? 7. 7 what? 7 volt. Then LM79 0 negative what? Then you cannot mention because you are writing. Look. Mexina, look. Yes, Mexina and Shukuru. They are right. Dixon, LM what? The boss. Hawezi kutaja. Hakuwepo darasani. Zemrudisha. LM 70 9 1 Eh? Omolo? Next is what? Somolo was not there. Mfunye? Suleiman? This is provide what? Negative 12. Negative 12 mangoes. 09. Okay. So now Johanna is in the class.